All right, good afternoon. All right, so apparently some students are not aware there's a homework due tomorrow. Is it tonight? No, so that was the first announcement I was gonna make. So I'm going to extend the last one, which is homework 7, was it? For resistor bias. That's the material we learned previous week. Okay, so that one's fine. But the next one, which is based off of the 4 resistor, bias and the other, there's 2 or 3 problems in there. And so, yeah, that's the one that's due tomorrow. So I'll extend it until Saturday. Yeah, so that's the first thing I wanted to. I should have just let students sweat it out for a few more minutes before. Well, he is on top of things apparently. All right, let's see. I think I recorded all of that. So yeah, recording's already on. Okay, so today we will begin op-amp circuits. So let's go into chapter number 3. Operational amplifiers. Okay, they are so called because they are used for a variety of operations, analog computers when they first came out. Okay, let's see. So question is being asked about homeworks 8 and 9. Yes, so depending on how fast or slow we cover the material, I always change the due dates. Okay, so you do not have to worry about only having a few days to do the homework. But again, keep an eye on all the homework assignments because most of them have been posted earlier this week. Okay, all right, so saying op amps. Well, let's look at a standard amplifier, right? Ideal amplifiers have functions and they find applications for like signal amplification, filtering, impedance matching, sorry, not impedance matching, impedance isolation, where we want to isolate, two cascading circuits, from the source and the load. So some examples of amplifier applications are in audio processing, right? We have your audio video receivers, in consumer electronics, where you connect all of your electronic devices into a single unit, and then that single unit is connected to like multiple speakers, right? So that's an example of where you would have an audio amplifier. Then measurement sensors, comparators, oscillators. Oscillators are basically used to generate time varying signals, like AC signals, sinusoidal signals. Comparators basically are used to compare an incoming signal with a preset level of signal. So based on the difference, it compares and provides the output. So either outputs on or off, depending on the difference of the input signals. Anyway, these are just common functions and applications of an amplifier. So several decades ago, when we didn't have computers, they were working with analog computers, right? Analog computers. Now, these computations, would require like physical devices that would fill up like an entire large room, like this one. Okay, so you had analog computers that would like typically fill up this entire room. As we went along, technology improved, and of course, we started shrinking down the size of the devices. So one of the earliest solid-state devices was basically the operational amplifier. Okay, it had about 25 to 30 transistors, a few resistors, built into a single chip of silicon. Okay, single chip of silicon. Now, we don't look at the internal workings of the op amp. We don't even do that for EE major classes, right? Even for the EE major classes, when they first come in the first year, we look at the terminal characteristics, and that's even more true for EE 321. What we are interested in is basically the behavior of the op amp at its terminals. Okay, so we will look at that. This pin out right here and this configuration of the circuit configuration belongs to the most popular op amp chip, IC741. And that's the one that you have used in the labs. Okay, IC741. Even when I was studying op amps, this was way back in the early 90s. I studied op amps with an entire course was devoted just to an op amp, like an entire year-long course. And the only thing we studied was different circuits built with 741s. Okay, op amp circuit with 741. So it is by far the most popular op amp circuit. All right. So again, the op amp, the name comes from the variety of operations that the circuit can perform. Okay. So operational amplifier, or op amps for short, basically can be used in a variety of applications. As engineers, whether you are EE major or non-EE major, you're expected to analyze, for the voltages and currents, but more importantly, you'd be required to understand how you can take a pre-built op-amp chip and design a circuit for a particular application. Okay, so that's why we are more interested in the terminal characteristics of the op-amps and not so much the internal. All right. And op-amp uses, typically like, for other amplifiers, it has a variety of uses. First and foremost is amplification, as the name suggests. So you give an input signal to the op-amp, and in the output, depending on the gain and the circuit configuration, you have a larger output, right? So if you give an input of, let's say, 0.1 volt, depending on the circuit configuration, we might have like 10 volts at the output. All right. Now, again, remember from the BJT chapter and the topic of amplification, you can give a small AC signal, and the power to amplify this comes from the DC power supply. The DC power supply, right? So AC, small AC plus large DC gives you a large AC signal. And that's the point of amplification. You give a very small AC signal to the op-amp will take its power supply, combine it with the AC signal, give that power and energy to that AC signal, so you have a larger AC signal at the output. That's what it's doing. The other major application for an op-amp is in filtering. So in EE201, you learned about passive filters, and they're passive because we simply use capacitors and inductors to filter out unwanted components. The reason they're called passive is because there is no active component in there. Op-amp is an active component, so we can use capacitors along with the op-amps to create an active filter. Okay, active filter. And what the active filter does is it performs the task of electronic filtering, and it also provides gain. Okay, so one of the applications that would be in consumer electronics is the graphic equalizer. If you've ever seen a boombox with manual sliders, right? That's an example of an active filter. Okay, that's an active bandpass filter. So filtering, amplification, and of course, it also performs mathematical operations. The two most common ones, well, actually, it can perform all four. So you have summing amplifiers, you have differential amplifiers. Op-amp is nothing but a differential amplifier. So difference amplifier, a summing amplifier, and then the other two common ones are differential and integration output. Okay, so you have a differentiator and you have an integrator operations using the op-amp. So summing, difference amplifier, differential, kind of the same thing, and integrator. And we will see later on in this chapter that some of the circuits are the exact same depending on the analysis we perform. So, the lab this week, by the way, how many of you have already finished the lab? Okay, most of you have. But the lab, it says, what kind of filter is it? It's a low pass filter and an integrator. If you analyze that same circuit in the time domain, you can say it works as an integrator because it integrates the input and gives it to the output. If you analyze mathematically in the frequency domain, meaning you're only considering the frequency of the input, then you can say it functions as a low pass filter. Okay, it's the same circuit, it's doing the same two things at the same time. It depends on what you're interested in, right? Integration is basically the incoming signal, you're just integrating between the limits of the time period. Frequency is if the incoming signal frequency is varied, meaning it's going very high or very low. Depending on that, you can use it as a low pass filter. So again, depending on what kind of analysis you want, what kind of application you want, the same circuit can perform more than one function. And well, that leads me to the point statement saying that it's a versatile building block for many applications. Okay. One of the other core applications is using it as an instrumentation amplifier. So when we have very precise measurements that we want to make that are not sensitive to that are very sensitive measurements, then we use these kind of instrumentation amplifiers. So when we have a small incoming signal, we'd use a amplifier circuit built with an op-amp, and hence the name instrumentation amplifier. Let's see. Standard symbol for standard symbol for an op-amp is a triangle, typically pointed towards the right. Okay, it's a triangle pointing towards the right. Now, most books, most authors, most professors will use something like this. You have two terminals going into the op-amp and one coming out. Okay, there's a plus sign at one input and a minus sign at the other input. The plus sign indicates a non-inverting input, and the minus sign indicates an inverting input. And again, you have one output. So at its most basic, the op-amp is a differential amplifier or a difference amplifier. Okay, it takes the incoming signals at both the inputs and it amplifies the difference. Okay, it amplifies the difference between the two signals. And you have one output, V out. Now, if you, let me take you back here. Here and here. You have two power supply rails, positive as well as negative, And that is there primarily to actually allow the op-amp to swing in both the positive as well as the negative directions. And so it's able to faithfully amplify the positive half cycle as well as the negative half cycle. Okay, so the power supply terminals are typically not shown in an op-amp circuit, but if they are shown, they'll be written like this: plus VCC, or simply plus V and minus V. And those are typically referred to as the power supply terminals or power supply rails. Most op-amp circuits, we will not show the plus and the minus V. Okay. Also, if you see a typical amplifier circuit, the minus or the non-inverting terminal, the inverting terminal will usually be up top, and the non-inverting terminal will be at the bottom. So in the symbol here, standard symbol from the book, you see plus up top and minus at the bottom. But when we actually build the circuits, if you've already worked with the labs, you have seen these op-amp circuits, you have a minus up top, plus at the bottom. It does not really matter, but it's a small distinction that you should be aware of when you're actually looking at a circuit. Oftentimes we get used to drawing circuits a certain way, and then when we see a connection, we think a circuit is doing one function while it's actually doing something else. And the reason it's important is because we'll actually look at feedback from the output going back into the input. So depending on whether it's connected to the inverting terminal or the non-inverting terminal, we'd have either a negative feedback or a positive feedback. Okay, and we'll talk about that in just a few slides. Anyway, so this is V out or VO. This would be V minus, or sorry, not V minus, inverting terminal and non-inverting terminal. And non-inverting terminal. So primarily, we can say an open loop op amp, which does not have any feedback coming from the output, has two modes of operation. You have the common mode operation, and you have the differential mode operation. Common mode operation basically means that the same signal is going into the two terminals. If not the same signal, very similar signals going into the two terminals. Okay. So the actual signal going into the op amp for a common mode operation would be the average of the two, half of V1 plus V2. And when I say V1, V2, it's right here. Okay, V1 plus V2. And when it's differential mode simply means the difference between the two terminals. And so it's V1 minus V2. The non-inverting input minus the inverting input. You're still adding them up, but the inverting input is minus. And so it's V1 minus V2. Let's take 10 seconds. Let me know if you have any questions. Yes.
They have any signal when they say that they're going to be a common mode or differential mode to the specific video?
Like you mean in the problem statement? Like yeah, you can simply know it. Yeah. Yes. No, that's going into the op amp. That's going into the op amp, not the output. It's still just going into the op amp. So we have two inputs, right? So an op amp is seeing going into the op amp. This is what it sees. If you have two inputs and both of them are the same, the common mode input is basically going to be average of the two. So half V1 plus V2. And the differential mode input will be simply V1 minus V2. Sorry, V1 minus V2. Yes. Well, that's just the inherent property of the op amp. Yeah. Well, the thing with, yes. So common mode and differential mode is basically, we can say it's an inherent property of the op amp. Okay. Well, not even inherent property. If we have two terminals to an input device, right? No matter what kind of device it is. Let's say, for example, we have a measurement instrument, right? We're trying to measure something. Now, if you're trying to measure something, there might be noise present in the surrounding air, right? Or it's picking up something through the wires and the cables. Now, if you have two inputs going in, and one of the inputs is held at a certain level, let's say, right? A fixed level. So that level is known. Then we take the incoming signal and we are trying to compare it to the known level so that we can figure out what level this incoming signal is at, right? So an application of comparator, for instance. So at that point, the op amp has a difference of input signals that are going into the terminals. But any noise signal that is present in the surrounding cables or in the air will be common to both terminals. So that noise signal would be the common input that's going in, whereas the fixed signal and the incoming input signal would be differential input. Does that kind of make sense? Any signal that is common to both terminals is basically, well, is a common mode input or common input. And any signals that are different is basically just a differential. The op-amp will see both and have both modes of operation. But the property of an op-amp is that it will, let me go over here. It has infinite gain for a differential input, and it has zero gain for common input. So again, using the same example of a instrumentation amplifier or a comparator, if you have noise signals coming in here, those inputs are common to both terminals. And because they're common to both terminals, what the op-amp sees is basically an average of the two. Zero amplification for the noise signal, so it's completely eliminated from your measurement, whereas the difference between the two will be amplified. Okay, so it's not as if we are applying that common input on purpose. It is the inherent property of an op-amp that any incoming common signals it sees at both terminals will be basically amplified by zero, or basically rejected. There is a term associated with this, and I'm now jumping a little bit ahead and going on the side. It's called common mode rejection ratio, CMRR. That is the spec of every op-amp circuit. Okay, it basically tells us how good the op-amp is at rejecting a common mode signal. Meaning, if the same signal appears at both input terminals, those signals should be rejected. All right, does that make sense? Does that answer your question? I know there's still some confusion, so please feel free to ask. The biggest example is noise rejection. Noise rejection. So in electrical engineering, any unwanted signal, any unwanted voltage or any unwanted current is referred to as noise. Okay, so even again, using the microphone as an example, if the microphone is capturing my sounds, any other external noise should be rejected. And so to reject those noise, we use this kind of circuit, because if it's common, then it should be rejected. Yes, you have a question? Okay. But basically, the op-amp has an inherent property. So if signals are common to both terminals, we say it's a common mode signal. If they're different at both terminals, then it's the differential mode. And the op-amp inherent property, doesn't matter what kind of op-amp it is, that op-amp's inherent property is that it has zero gain. An ideal op-amp has zero gain for common mode signals and infinite gain for a differential mode signal. So if we were trying to measure a very, very small signal, we would reject any noise that appears at both terminals and amplify only the difference. And that's why, again, that's one of the beautiful points about the op-amp function. Okay, so op-amp has the inherent property of having infinite gain in open loop. When I say open loop, meaning the output doesn't loop back into the input, whether it's negative or whether it's positive. If you connect the output back into any one of the input terminals, we say that it is providing feedback. Okay, so absent any feedback, we say that the op-amp is operating in open loop mode. Okay, open loop mode. So open loop meaning no feedback whatsoever. No feedback from the output terminals. And the op-amp property is that it has infinite open loop gain. Okay, infinite open loop gain. Gain is noted by the letter A. So open loop gain is referred to as AOL. AOL. Okay, open loop gain. Questions? Any questions? Okay, so the equivalent circuit of an op-amp can be described as you have Non-inverting input V1, you have inverting input V2. The actual signal going into the op amp is a difference of the two. So it's V1 minus V2 on the input side. And on the output side, what we have is a constant voltage. That constant voltage is basically the differential input times the open loop gain. So V out is a constant voltage, which is the differential input times the open loop gain. And so it is modeled as a dependent voltage source. Okay, dependent voltage source. And if you remember from 201, we introduced dependent sources, not do any analysis. So again, this is just a model. It's a dependent voltage source. It'll give you a constant output voltage, but that voltage is dependent on VID. And the multiplication factor is given by the open loop gain of that op amp. Yes. A is gain, yes. And OL stands for open loop, meaning there is no feedback coming from the output back to the input terminals. So what are the properties of an ideal op amp? Ideal op amp has infinite input impedance. Again, doesn't matter what kind of op amp it is, the design of the circuit and the construction of that circuit determines that it has infinite input impedance. At the same time, it has zero output impedance, which is actually what we want in most circuits. Okay, we always want to have infinite input impedance and very low output impedance. In case of an ideal circuit or an ideal component, it's infinity and zero. Infinity and zero. The reason for having infinite input impedance is so that if you have your amplifier circuit, and you have incoming signal, if the amplifier has very high input impedance or infinite impedance, then it is not pulling in a lot more current from your source, because your source is basically this, right? So you want to minimize the current that is being fed into that op amp. So that's the reason we want infinite input impedance, or as high of an input impedance as possible. On the output side, however, you want it to be as low as possible, so as to able to drive maximum amount of current to the output. If you think in terms of the AVRs that we have, and you connect a speaker, unit to your amplifier, a speaker unit typically has impedance of around 8 ohms or so. So you want the output of your amplifier to match the impedance of those speakers, which is typically around 8 ohms. So as low as possible. When you have it as low as possible, you can drive as high a current as possible through your amplifier circuit. And then, of course, the other 2 points we addressed, where you have infinite gain for a differential input and zero gain for the common input. Now, again, as I said, on purpose, most circuits are not designed on purpose to actually have common input going in. Okay, the property of an op amp is to typically reject any common inputs, and the most common application is for like noise rejection. So if you have any kind of noise signal coming in, that noise is present in the surrounding air or surrounding electronics, then it will be present on both input terminals. So it's common to both input terminals. It'll just reject those those input signals. And then it has infinite gain for differential input, zero gain for common input, and infinite bandwidth, meaning you could apply a wide range of frequencies to this op amp, and it will amplify all of them the exact same. Real life, that's not the case. If frequency increases, open loop gain is constant for a while, and then it tapers off. Okay, it tapers off. So open loop gain will taper off for real life op amps. But ideal op amps, it remains constant. So infinite bandwidth in that sense. Okay, infinite bandwidth. Meaning you could give any frequency input to the op amp, it'll amplify it without any issue. So just by itself, if you were to use an op amp without any external components, what kind of filter would you say it is? Low pass. It's only allowing low frequencies to pass through. So in the spec sheet, there is a frequency specification that your op amp is good only for certain frequencies. But that is only for open loop gain, meaning just the op amp by itself without any external circuitry. Now, typically, we would use a few resistors, some capacitors, depending on our application. All right, questions. Does it make a little bit more sense now? Common mode, differential mode. Okay. Again, as I said, for most of these topics, we can go really deep into each one of those and have like a semester-long course about it. When I studied it, I specialized and I had like a year-long course just on op-amp circuits. So there's a lot more things we can do. But as engineers, you should be familiar with the terminal characteristics. You should be able to like just take a device and be able to analyze what kind of circuit it is and analyze the circuit and determine if it fits your application. Okay. Again, continuing with ideal op-amp, a little bit of the internal circuitry. We have a inverting input terminal up here, so it's negative here, it's positive here. Since we say the op-amp has infinite input impedance, Zin, the input impedance of the op-amp between the two terminals, is said to be infinite. So Zin is infinity, whereas Z out would be 0. Now, of course, if it's real life, I would say it's approximately infinity, and Z out is approximately equal to 0. And of course, it's a constant voltage source that is amplifying the differential input with the gain A. Okay, gain A. Now, V out, of course, as I said, it's V plus, so non-inverting input minus the inverting input times the gain. If you notice the two currents that are going in, if it's infinite impedance, what can we say about these currents? Exactly, so they are 0, right? So ideal op-amp is not going to pull any current coming in. There will be a voltage difference, but it's not going to allow any current to actually go into the op-amp itself. Okay, so if there's no current going in and it's infinite impedance, we can say that both currents are equal to 0. So I plus, meaning the current at the non-inverting terminal and the inverting terminal are both equal to 0. If they're both equal to 0, there's no current that is flowing through Z in at all. Okay, so there is no current flowing through Z in at all. And there's no current flowing through there. What is the voltage across Z in? If 2 points are the same potential, no currents flow through there, right? So if no currents are flowing, we say both ends or both points are exactly at the same potential. All right, and that's why we can refer to both terminals as having the exact same potential. Okay, we refer to the inverting terminal V plus as equal to V minus. So inverting input and the non-inverting input will both have the exact same voltage. Now, there are certain assumptions we make. This is ideal op-amp. Real life op-amp obviously will not have ideal impedance. There will be some current that actually goes into the op-amp, but it'll be very, very small. When we analyze the circuit, we will still assume we will keep these rules. We will acknowledge these rules and we'll analyze a circuit based on these rules. And the rules are that it has infinite input impedance. Current going into the inverting and non-inverting terminal are equal to 0. And the voltages at both terminals are also the same. Okay, so I plus is equal to I minus, V plus is equal to V minus. And we call this concept as a virtual short. A virtual short. So it is known as the concept of virtual short. It would be just the same to say that it is virtual short and virtual open. You can look at it in both ways and both of them would be true because current is 0 and voltage is the same. Okay. All right, let's take 10 seconds. Let me know if you have any questions. Yes, question? Okay. Excuse me. We good so far? Yes. It's not a condition as much as a assumption. Mostly it's called virtual short, but I'm saying at the same time, you could also say it's virtually open. Yeah, both of them would be valid. I know it seems contradictory, but both of them would be valid at the same time. Virtual short because we are considering the voltage to be the same, but if the current is not flowing, it's also open, right? Infinite input impedance, so no current is actually going in. The only way a current is equal to 0 is if, well, if there's no pathway for the current to flow through. So we can say it's virtually open. And then of course we have our plus and minus voltage supplies. So that was open loop, right? Open loop. However, amplifiers are typically used with feedback. And what we do with feedback is we take the output and we feed it back into the input so as to control the operation of our device. Okay. There are two kinds of feedback. If you take the output and connect it to the non-inverting terminal, which is a positive terminal, we say it's positive feedback. If you connect it back to the inverting terminal, which is the negative terminal, then we say it's negative feedback. So if this is output, this is the negative terminal, output goes in here, is negative feedback. If output goes into the positive terminal, it's positive feedback. And both of them have their uses, but typically we would use an amplifier or an op-amp with negative feedback. So most of the circuits that you would look at will always have negative feedback. Negative feedback has the effect of actually reducing the output. Okay. So negative feedback again goes into the inverting terminal, and so it inhibits the amplification, and its positive feedback, it reinforces, it's amplifying, and then it drives it into hysteresis, and we can use it we can use it as an oscillator to generate AC signals. So oscillators are primarily formed from amplifiers with positive feedback. Now, one word about positive or negative, right? The reason we say it's inverting and non-inverting is because there is a phase difference of 180 degrees between the input and output, right? Remember for EE201, if both the input and output have exactly the same phase, we say, well, the phase difference or phase shift is 0 degrees, non-inverted. But if the phase is shifted by 180 degrees, something like this is now like this. It's completely the same, but it's out of phase by 180 degrees. We say it's the inverted. Yes. Inverting. Negative is inverting. Positive is non-inverting. So invert in this case, well, not in this case, but in general case, invert means the waveform that you have is out of phase by 180 degrees. Okay, 180 degrees. In a real life example for that would be your noise cancellation, right? Noise cancellation. So if you have a signal like this and you invert it, so it now becomes like this. What happens when you add them up? Output goes to 0, right? So that's noise cancellation. So you take, if you have noise cancellation headphones, what they're doing is they have microphones that capture the ambient noise, invert its phase by 180 degrees, meaning you take and apply to the negative inverting terminal, add it up to the original signal, output goes to 0. And so if you, noise cancellation headphones, yeah. Even any old phone that you would, even the flip phones that you would take, there's a microphone right next to your speaker. And the reason there's a microphone next to your speaker is because if you're holding a phone trying to listen to the person at the other end, you don't want any ambient noise to come in. And so the microphone that is right next to your earpiece or the speaker is going to capture the external sounds. That microphone sounds which are captured are inverted in phase by 180 and added back onto that input signal that goes inside the smartphone or inside the phone. And when it's output to the speaker piece, it gets canceled out. That's basically how noise cancellation headphones work. You take your incoming signal, you invert its phase by 180, add it to the same input signal, and you zero it out. That's what negative feedback is doing. Negative feedback takes the amplified output, provides it back to the input, so it reduces the the input signal at the negative terminal. So that's why the op amp cannot just constantly keep amplifying and drive itself into like saturation. Any questions? So here's an extreme example of negative feedback. Okay, extreme example of negative feedback. You simply take the output and tie it back to the inverting terminal. Okay. Near instantaneous operation of the circuit. I mean, the explanation takes a while. The analysis takes even longer. So you can do an in-depth analysis, but just to explain in a few brief steps. This is what kind of amplifier is this first? It's an inverting differential amplifier, right? It's an inverting amplifier. No, I'm just seeing how many of you are paying attention. Where is the input going? Input's going into the positive terminal. So if the input goes in the positive terminal, it's a non-inverting because it's going into the non-inverting input. So it's a non-inverting amplifier. So non-inverting amplifier with negative feedback, right? So that's the two things you should notice first. Input is going into the non-inverting terminal, so it's a non-inverting circuit. And feedback is going into the negative terminal, so it's negative feedback. So non-inverting negative feedback amplifier. Now what happens is, any input that's common is of course going to get rejected, right? So we only worry about the difference. So the difference is when V in, basically this right here, let's say we start off at 0. V in increases, then V out would correspondingly increase, right? It's amplifying, right? It's A times the difference. But that output at V out is fed back into the input right here. So what happens then? It decreases, right? So it decreases. So when it decreases, it's going to take that small difference and again amplify it. Remember, common signals, zero amplification. Difference, even if it's a very small difference, will have huge amplification. So it'll take that small difference, again amplify it, and again sends it back to the input. And that happens constantly, keeps happening constantly. Again, this seems like a long explanation, and I can tell you the analysis in terms of voltage and current is even longer. But suffice to say, anytime you change the input, the output keeps following the input. The output keeps following the input because input comes in, gets amplified, output gets sent back to the input. So the difference between the two terminals decreases, again gets amplified, again sends back to the input. And the output keeps following the input. So this circuit is also known as, we all looked at it in the lab, voltage follower. Yeah, I think that was one of the pre-lab questions, right? Voltage follower. This kind of circuit is especially useful when you want to isolate the output from the input. So if you have two circuits and we want to separate out the output from the input in the circuits, we would use this as a buffer in the middle. So this is also known as a buffer or isolation amplifier. It's an incredibly convenient and very powerful, effective circuit to actually separate out the input and the output. Okay. So again, as I say in the second big bullet point, the overall result is, doesn't matter what input it is, always take the difference of the input. The result is that V out will always go back to equaling V in. It might be slightly smaller, very, 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 very small difference between the output and the input, but near as we can tell, it'll be very close. So if you apply 5 volts at the input, your output might be 4.9999 something, but it'll be as close as possible. For all intents and purposes, the output is exactly equal to the input. And that's why it's called the voltage follower. Now, the reason that we use this circuit is so that we can isolate multiple parts, right? If you have RL in a circuit, let's say you have a circuit like this, right? With some output impedance, and it's connected to a load resistor. So the way we would model this, this is the driving circuit, this is load RL. If RL is small, what happens? If RL is small, what happens? This is the driving circuit. This is the current that's coming. This is the circuit. This is the current that's coming from the driving circuitry. Like R1 belongs to the input, RL belongs to the source. If RL, the input impedance of the load, is small, what happens? Most of the voltage will be dropped internally in the source itself, right? The voltage across RL will be very, very small. Voltage division or Ohm's law, V equals IR. So if RL is small, the voltage that should have been delivered to RL is no longer being delivered. Okay, so we isolate we isolate RL from its previous circuitry by inserting this isolation buffer in there. So the input, the output of R1 is given to the isolation buffer, and the output of the isolation voltage follower is given to RL. Let's see how, I'm already over time. So let's stop right here, and I will continue on with this example just to illustrate. It'll just take a few more minutes. So I will talk about it on Friday. If you have any questions, I'll be in my office. I have lab from 3 to 6 today. Again, if you want to stop by the office, you want to meet on Zoom, I will be available.